Hi everyone, and welcome back to another AP Calculus video. We're going to continue talking about Taylor polynomials and Taylor series. And really the difference is a polynomial stops at a certain spot, a series keeps on going and has an infinite number of terms. So in the last video we discussed how any function can be expressed as a polynomial if we know the behavior at a certain point. Now so far we've seen the behavior at 0 because that's a nice easy one to start with. We like zeros. And so at 0, we would have a function like this. So if we know the behavior at a point, in general, this would be the polynomial of x. This would be centered at x equals 0. Notice all of the values, all of these coefficients involve finding the derivative at 0. And the cool part is what we're doing is we're saying, hey, we know that this function we want to model has this behavior. We know the first derivative, second derivative, and third derivative, and so on and so forth. Our polynomial has the same derivatives at that spot. Now, as we move away from that spot where x equals 0, we're going to find that our polynomial doesn't quite line up. And the more terms we have in our polynomial, the better of an approximation it becomes. In this video, we're going to take a look at the graph, and we're going to see how they line up. But in general, if we're going to do a Taylor series centered at 0, we also can call that a Maclaurin series. Now, a Maclaurin series is pretty much a series centered at 0. Taylor series, we're going to see, can be centered anywhere. And so Taylor is credited with taking that series and kind of shifting it around. And so if we look at this notation, let's just understand that we generally like our series to start at 0, so we do try to make it start at 0. If yours doesn't start at 0, that's okay. As long as your notation lines up and it's proper and your nth term lines up with your first term. So there's not going to be a penalty if you start your series at 1 and it's supposed to be at 0, unless the original problem starts out at 0. Then you might run into some trouble. But in general, you've got this. Whatever n is, we take this f to the n power, that's not a power, sorry. F to the n, that means the nth derivative. So when n is 0, here's why we like to start it at 0. When n is 0, that's just saying we haven't done a derivative yet. And then notice we have n factorial, and then it's x to the n power. So that's where the n's all are. So when n is 2, that means it's the the x squared term. You're going to have a 2 factorial in the bottom. Second derivative is going to be in that numerator. So if we are looking at this and we want to write a polynomial that approximates a function near x equals 0, here's kind of what it would look like. Let's review what we learned in the last session. So I need to know, first of all, the 6th degree Taylor polynomial means that I'm going to go up to a power of x to the 6th. That's going to be the biggest power in my function. So I need to know f of 0. I need to know f prime of 0. I need to know f double prime, f triple prime, the 4th derivative, the 5th derivative, and finally the 6th derivative, all at x equals 0. So let's use our wheel of signs. So we're going to have sine, cosine, negative cosine. So if we're starting at cosine, the derivative, so this would be cosine of 0. This would be negative sine of 0. This would be negative cosine of 0. This would be sine of 0, cosine of 0, negative sine of 0, and then negative cosine of 0. Yep, there we go. So here we go. We're going to have 1, 0, negative 1, 0, 1, 0, negative 1. And we have this pattern much like we saw with sine. But this time the zeros are on all of the odd derivatives. So let's see what this looks like. My 6th degree polynomial will end up looking like this. I'm going to do f of 0, which is 1, plus 0, that's my first derivative, x over 1 factorial, plus negative 1 x squared over 2 factorial, plus 0x cubed over 3 factorial, plus 1x to the 4th over 4 factorial, plus 0x to the 5th over 5 factorial, plus negative 1 x to the 6 over 6 factorial. Now when I clean it up, get rid of all my, all my zeros, my 6th degree Taylor polynomial for cosine looks like this. 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6 over 6 factorial. And so when I go to write my Taylor series, I would write it like this. I'd say, well, the cosine of x is equal to, in my sigma notation, and actually we'll do sigma second. Remember, there's two ways to represent a series. You can either write out the first few terms, a lot of writing, plus dot dot dot, and then we're going to throw that general term in there. So it seems to be x to the 2n over 2n factorial. These are even powers, and yes, there's an alternator in there. So which terms is it? Well, if we're starting at n equals 0, the first term is positive, so there you go, n equals 0, it's positive. The second term would be, let's see, when n is 0, when n is 1, because remember, we reset, we say, hey, let's let n equal 0, n is 1, n is 2. So remember, we're saying, hey, 2n, we're taking into account, we're skipping the odd terms because we made x to the 2n. That gives us our even powers. So that means when n is 1, I should have a negative. So negative 1 to the 1 power gives me my negative. So always check to make sure your signs line up. Plus dot dot dot. So that's my cosine. That's one way to represent the Taylor series. Another way to do it is to say sigma notation. So you go sigma n equals 0. And then all you do is just throw that nth term in there. Ta-da! And that's all we have to do. So both of these are totally fine. The key is you would have to have sigma notation and the general term, or the first several terms and the general term. Keep in mind your free response will sometimes just say write out the series, make sure you give the first few terms. In that case, you'd have to write out the first way. Sometimes sigma notation is acceptable though. But this is how we construct our Taylor polynomial. And again, it has to do with knowing what the derivatives are. And if we were to do the derivatives of this polynomial, it would have the same behavior that cosine does. Now, let's take a look at a little illustration for what we just did and kind of show you the polynomial that we just built, how it lines up with cosine. Now here I have graphed cosine, and you can kind of see in the red, that's the cosine curve. So let's make it nice and easy to read. So here's my red cosine curve, and here's the polynomial. Now what I've done is I've put the sigma notation in, and I'm allowing you to see, okay, if a equals 1, this just means we have an x squared term. So you can see we have an upside down parabola. It's an x squared term. Now as I move a along, notice what happens. All of a sudden now it turns to an x to the 4th power, because remember, x to the 2n would give me x to the 4th power. I'd have a 4th degree polynomial. And notice that it lines up a little bit more with cosine. And as I keep adding terms, so a equals 3, so this means that I'm now up to n equals 3, which would give me an x to the 6th power. And then I add another term. This means I'm adding on a term of x to the 8th. And as I keep adding terms, notice what happens. The polynomial starts to line up with cosine more and more and more. And you'll find that it's an exact match until it's not. And then it's really not an exact match. And if we just allow this to kind of play out, you'll see it gets all the way. Now I had it stop at 20, and now it's going backwards, and it's kind of unraveling. You can see that as we have less terms, it lines up over a smaller period of time. But as we add terms, that's what a to the 14th, 15th, 16th, we're adding terms each time. It's making it a better model for cosine. Now another way to do this would be to take my polynomial and actually write it out. So let's take a moment and kind of see what that would look like. If I were going to write this out, it might look a little something like this. And so you can see here we have our polynomial. I started writing, it's in green, and it should line exactly up right now with the blue function. So if I kind of turn them on and off, you'll see the green function lines right up. And if I just keep adding those terms, x to the 6th over 6 factorial, and then plus x to the 8th over 8 factorial. And if I keep on going, so let's see, this gets me up to this far, right? So here they are, they're the same. So a is 4. But you can see that it lines right up. And as I add a term and add a term and add a term, it becomes a better and better approximation. So you can see that if I have an infinite number of terms, this green curve would eventually mold to that cosine curve. And it's pretty cool. And we're going to see that the interval of convergence for sine and cosine happen to be the same thing. So let's see if we can get this kind of turned off here. Go back to our main screen. Now that we know how to construct a basic polynomial, let's talk a little bit about how this is going to kind of help us moving forward. Now we know that cosine of x is simply 1 plus and then, 1 minus, and then all the even terms. So we have x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. And then that general term is negative 1 to the n x to the 2n over 2n factorial. Now, suppose we wanted to construct the polynomial or the series, whatever the case may be, we wanted to construct something for cosine of 2x. Now here's the cool part. If I consider this to be a generalized cosine of x, perhaps I might generalize it by saying, well, instead of x, what if I think of all these x's as just being thetas? And I'm just going to kind of think of them as, thetas. Or better yet, what if I just say u? We like to use u a lot in calculus. No matter how you think about it, here's what's cool about these Taylor series and Maclaurin series. There's a handful of them that we need to memorize, and so far we've seen sine and cosine. Those are two of the most common series that we're going to see floating around on the AP exam. So if I wanted to construct a Taylor series or a Taylor polynomial for cosine of x, for cosine of 2x, then what I might do is I might say, well, if I consider this to be a generalization, for cosine of 2x, all I would need to do is if I know this formula, if I know what the cosine of x is, I can consider the x's to be thetas. And I can simply write it like, instead of theta, I'm just going to put a 2x in as my theta. I'm going to substitute theta equals 2x. And I get a polynomial that looks like this. 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial. Now this said write the 6th order or 6th degree. I want you to understand order and degree for our purposes do mean the same thing. It just means let the highest power be x to the 6th. And if this is the case, well then I've just constructed my polynomial. And this is all I need to be able to do. It's pretty awesome. So if I wanted to do something like cosine of, 5x plus 1, I would simply let theta equal 5x plus 1, and I would literally plop 5x plus 1 in for that theta. And it would look like this, 5x plus 1 squared over 2 factorial plus 5x plus 1 to the 4th over 4 factorial minus 5x plus 1 to the 6th over 6 factorial. And that's all there is to it. Now, suppose I also wanted to, while we're at this, suppose I wanted to deal with, finding a derivative, for example. So if I wanted to find the polynomial for f prime, if f of x equals the cosine of 2x, here's the glorious thing about what we just discovered. I already can construct the polynomial for cosine of 2x. I just did it. And it's this guy right here. But if I want to find the polynomial for the derivative, the best part about this is that with Taylor series and Taylor polynomials, all I have to do is literally take the derivative of the polynomial. It's the easiest derivative we ever knew how to do, polynomials. And all I have to do is do the derivative. So step 1, I'm going to take this function, cosine of 2x equals 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial. And to find the derivative, f prime of x, supposing that this is f of x, is literally the derivative. So, hey, 1's going to go away, it's a constant. But then here I'm going to have negative, I'm going to multiply by 2, but I'm going to have some chain rule going on too. So be careful, I've got to multiply by the chain rule. So I'm going to have 2 times 2x times 2 over 2 factorial plus 4 times 2x cubed times 2 over 4 factorial minus 6 times 2x to the 5th over 6 factorial times 2, that chain rule of that inside. And if I just kind of simplify that, then I've just done my derivative. So really it kind of turns into this nice, easy little thing. Now I multiplied everything out, but again on the AP exam, especially if it's a non-calculator portion, you could just leave it kind of like this right here and be just fine. Just be careful to make sure that you give as many terms as the directions indicate that you should. Sometimes you have to do an extra term, which is fine. You just continue the pattern. So what this tells me is that if I know a Taylor series for a general function, we can use substitution instead of just reconstructing the series from scratch. So common series include sine of x, cosine of x, e to the x, which we'll get to eventually, and a couple others that we've already seen that are more like geometric formulas. So 1 over 1 minus x, 1 over 1 plus x. These are all really common functions that we're going to see. Now these two are geometric, where a equals 1, and you either have r equal x or r equals negative x, which gives us an alternating series. So suppose we had something like 1 minus 2x. You would simply use the same procedure, and into that series you would replace x with 2x. So start thinking of these series as kind of an, a generalization. 1 minus u, 1 plus u, sine of u, cosine of u, e to the u, and if u is some function of x, simply replace the u with the function of x. Makes your life a lot easier, makes it go a lot faster. We'll be practicing this as time goes on. But now what we want to do is we want to take a look at what happens when we want to construct a Taylor series that is not centered at 0. Because remember, when we talk about a Taylor series, in particular the one we just kind of discussed here with cosine, and if we take kind of another look at what that graph in Desmos might look like. So here in Desmos, we're looking at that cosine of 2x again, because I wanted to just make sure that you understood and could see that when we just literally plop 2x in for x in that generalized cosine function, we get a function that lines up with our cosine of 2x curve. It's pretty cool, and it makes it nice and easy to construct some of these Taylor polynomials. But you'll see here we've got these functions. The red is the original functions, the blue is the Taylor polynomial, and you can see that up through the power of 6 it converges really close to this center x equals 0. Now if I wanted to find an approximation, you'll see that on the screen I've got a red point 0, 1, and I've got a blue point, which is the polynomial approximation. And what I want to show you as I hit play here is that as you move along, you'll see that the 2 points are very close up until about, let's see, they're close up, and they started to kind of diverge from each other not too far after about 0.5. So they were really close, and now they're really kind of like veering off from each other. And so what I want you to understand is that as long as we're close to the center, the polynomial provides a fairly accurate representation of the points. But to get a more accurate representation, I would literally have to take and continue adding. So if I add on here 2x to the 8th power divided by 8 factorial, you would see that it would line up for a little bit longer. And it would go past 0.5, and it's still the same. Oh, we're getting there. Same. Oh, it just started right about in there. You could see kind of that it started to diverge a little bit. So the more terms we have, the more close my approximations are. Now keep in mind that these polynomial approximations may not even be exact, they just are precise up to more digits. So you could see here going to 3 places, we had a pretty good amount of precision up to about, 1 away from that center. But to recenter this, suppose I wanted to use my polynomial to, approximate something a little closer to x equals 2. Well, how would I go about doing that? Well, the answer is this. Instead of centering my polynomial at 0, I would center it at x equals 2. Or I'd center it at x equals something closer to 2. Maybe I'd even shift it just to x equals 1. And then by centering my polynomial around a different spot, I can shift that accuracy, that window of accuracy, right along that x-axis, and I can get accuracy, I'm going to have a window, but since I can't expand my window, I'd have to put so many terms in there to expand my window. Rather than expand the window, we just shift it. And that's what Taylor kind of came up with when he was trying to decide what to do with his polynomials. Where a Maclaurin series is always centered at 0, Taylor found a way to center his polynomials at values other than 0. So let's take a look. To center his polynomials and his series at something other than 0, Taylor said, well, first of all, I need to know the behavior at that spot, wherever my center is. So he began by calling it A. He said, A is going to be our new center. And so you'll notice that it's the same basic layout where instead of having, x to the n, we now have x minus a. And what this does is it says, well, at a, when x is a, my polynomial and my function should be exactly the same. He also, notice, has the derivatives at that point a and the values at a. The one difference is that instead of x to the n, we're going to always have x minus a to the n. So if we wanted to construct a Taylor series for f of x equals e to the x, centered at x equals 2, we would kind of go about it the same way that we would, constructing any other Taylor polynomial. We would need to know what f of 2 is. We'd need to know f prime of 2. We'd need to know f double prime of 2, f triple prime of 2, and so on and so forth. Now let's just start with these first 4, values here. We know that the derivative of e to the x is always e to the x, so that's really nice. So e to the 2 is going to be f of 2, and it's going to actually be the same no matter where we are because the derivatives are it's just e to the x, e to the x, e to the x, so that's really nice. So now my Taylor polynomial, or my series, is going to look like this. F of 2, which is e to the 2, that's this one right here, plus f prime of 2, well that's e to the 2 times x minus 2. And then the next term looks like this. We'd go plus e to the 2 over 2 factorial, and then we'd have x minus 2 squared, plus e to the 2 over 3 factorial times x minus 2 cubed, plus dot dot dot, plus, now we need our nth term. Well, it's always going to be e to the 2, and then you're always going to have x minus 2 to the nth power. It'll be over n factorial plus dot dot dot. So there's my Taylor series that is centered at 2 for e to the x. So it's pretty nice. You could also write it in sigma notation and just go n equals 0 to infinity, and then just put that nth term in there. That would be another way to construct the series. Remember, we can express a series in more than one way. We can express it as a list of terms with a general term tacked in there, or we can do sigma notation. So anytime we do a Taylor series, you have to pay attention to where we are centered and what's happening in general with the polynomial. So we now want to use our answer. Suppose we want to define the Taylor series now centered at 2 again, but this time we want it for e to the x squared. So now we're going to kind of put things together and go off that principle that we talked about earlier that said, hey, if I know the general rule for e to the x, I can just take x squared and plop it in. So think of it as a u substitution. Now the key is it has to be centered at the same spot, which we happen to be. So I'm going to take the Taylor series and check this out. Literally all I'm going to do is I'm going to say, well, from n equals 0 if this is my Taylor series, then I'm going to go ahead and plop in my x squared, and I'm going to do the same rule that I did with my cosine of x and my cosine of 2x. And we end up simply with this. Literally all we're doing is we're taking x, replacing it with x squared. That's just kind of how it goes. And if you needed proof that this is how it works, we could take a look at the graph here in Desmos. And if we take a little peek at what's going on here, I've graphed the two. So here's e to the x squared, and literally here is the function where I just rewrote it with x squared instead of x, and I just went out to the third degree polynomial. Now you'll notice here the interval of convergence is going to be a little different, and actually it goes past the ones, and it has to do with the x squared, and we'll get into that. That's later on in chapter 9. But the idea here is it does converge. Check it out. Look, it's converging. Yay! It doesn't converge in the middle, but it converges beyond 1 and -1. So it's one of those weird kind of cases. And again, that's something we'll explore a little bit later on to see what that looks like. But I would encourage you, as you're kind of learning these things, to use Desmos as a checker. And when you graph the sigma notation, which, by the way, if you need to know how to insert the sigma notation for this, you would just simply need that nth term. And I'll kind of show you where the sigma is here in Desmos. So if you take a look right here, if you go down to right there, the little keyboard, you can kind of go to your functions. It's under miscellaneous, and right there, there's your sigma. So as long as you know where you're starting, n equals 0, up to, and now you can't type in infinity, right? So just go to like the 20th term. Anything beyond the 20th term, you might be getting a little crazy. But you just go e squared, and then you kind of go x squared minus 2 to the nth power all over n factorial. And there, whoops, you'll see it is diverging here. There we go. Oh yeah, so there it is. So we'll turn off the polynomial that this one goes up to like the 20th power. Check it out, they're the same. They do converge. So all you literally have to do is put the x squared in. So if I change this to, an x cubed, all I have to do is go here and change that to an x cubed, and I've created a convergent function. Now this one, it's not liking me right now. There we go. Takes Desmos just a little bit of time to kind of get things under control. You need to give it a little time too. But that's really all we're doing. So suppose we wanted to write, let's go ahead and change this back to e to the x squared. E to the x squared. Boom, that's all we have to do. We'll give Desmos a chance to kind of think. But suppose we wanted to take it one step further and we wanted to write a function for this. Well, literally, this is just saying 3 times the function plus 2. So quite literally, we're going to say 3 times that sigma notation plus 2. That's all we're doing. So if I wanted to write a rule for this, I would take that function, it would go e squared plus e squared times x squared minus 2 plus e squared times x squared minus 2 squared over 2 plus e squared times x squared minus 2 cubed over 3 factorial. I would take that pattern, let's say we're just doing the third degree polynomial. I would quite literally take this, distribute 3 to each term, and tack a 2 on the end. And it's as easy as that. And it turns into the 3e squared plus 3e squared times x squared minus 2 plus da 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 da, and then you add 2 onto the end. It's literally as easy as manipulating the series. So you can see what a powerful tool these are. And just as one final little demonstration of the power of what's happening here if I did happen to change my function to 3e to the x squared plus 2, you can see that if I just stick a 3 here, boom, and then I'm just going to add my 2 on, 2 plus, we'll see our series does in fact converge. You can see off and on, off and on. Now it does take a little while, so if I reduce this down to like 10, it might go a little faster, not much. But you can see that they do converge. It does line up quite nicely when I do this right. And so literally it's just a matter of distributing 3 to each term and then tacking a 2 onto the end. So that's what this sigma notation does. So these tools, these Taylor series, are incredibly powerful tools. It is so nice to be able to manipulate. And if you think about what you would have to do to construct the Taylor series for e to the x squared by taking derivatives, the first derivative would be 2x e to the x squared. To find that second derivative, you'd need to do a product rule. To find the third and fourth and so on derivatives, you'd have to continue doing the product rule, and it would just get incredibly cumbersome. And trying to construct them from scratch, while possible, is not a good use of our time. So understanding that if you can recognize the basic structure of a Taylor series, like e to the x, sine of x, cosine of x, 1 over 1 minus x, and 1 over 1 plus x, and then there's a couple others in there too. But if you can recognize these as some of your really common Taylor series and Maclaurin series, you can reconstruct a series for a similar function quite easily by just replacing the x with, in this case, x squared. You can also construct a series for a function if you know the series for e to the x, and then you can make e to the x squared. You can make a series for 3 times e to the x squared plus 2 by simply multiplying the series by 3 and adding 2. So these little tips and tricks are what the AP exam is going to try to test you on. The more you get used to using your Taylor series and the more you can recognize the common ones, the better off you're going to be in the long run. And the more practice you get with these, the better you will become. So my encouragement, as always, is to keep at it, is to keep practicing, do that homework, ask lots of questions, practice, practice, practice. You're going to get it. You can do this. You've got this.